Welcome, welcome, welcome. We begin electricity and magnetism. So, this is section D of the syllabus. Let's see, section D. I shouldn't even write this, I should just put Elec and mag. For those of you who did Elec Tech, nice time. For those of you who did not, it might appear weird, but it's not as hard as it sounds or seems. So, first of all, we have to define electricity, right? Electricity is basically the byproduct of charge being present and significant quantities of charge. There are charged particles, well, yes, charged subatomic particles, the proton and the electron. The proton is positively charged, the electron is negatively charged. Now, they have equal amounts of charge, but the charge is what we say opposite in nature. The charge on the proton is positive, the charge on the electron is negative. The minus and the plus, the negative and the positive, are only put there to indicate that the charges are opposite in how they behave. That's it. So electricity can be thought of as what happens when you have significant amounts of charge present. And this leads us to the first type of electricity, static, S-T-A-T-I-C, static electricity. Static electricity is basically electric charge, C-H-A-R-G-E, at rest. 1 second, folks. Now, static electricity is produced by one of two methods. Friction. I should probably write this in a different color. F-R-I-C-T-I-O-N, friction. If you rub glass with a dry cloth, or perspex with a dry cloth, or polythene with a dry cloth, one of those materials attracts negative charge and the other attracts positive charge. But that's one way of looking at it. Say I have a series of positive charges just chilling over here. That's a really bad example. I shouldn't say just positive charge and on. Say I have equal amounts of positive and negative charge, right? Positive and negative charge. And some of the negative charge goes over here. For whatever reason, I could say one of two things, right? I could say that here gained the negative charge, and I could say here lost it. So when it comes to charging or producing static by friction, we could say that one object gains the charge and the other object loses it. Either which way is correct. You don't necessarily need to say it both ways, but you get the idea. So the objects that are the syllabus expects you to know would be, well, the objects that are charged by friction that the syllabus expects you to know would be a glass rod and dry cloth, perspex rubbed with a dry cloth, and polythene, P-O-L-Y-T-H-E-N-E, and a dry cloth. The syllabus expects you to know these. Now, like I said, one will gain one type of charge, and the other, sorry, I just knocked my microphone down. One will gain one type of charge, and the other will lose the same type of charge. So if one becomes negative, it means that the other one lost negative charge. Getting that out of the way. The next method is by induction. Charging by induction. Now, what on earth does that mean? Charging by induction. If something is charged by induction, it is very simple. I get an object and I charge it by friction. So my object is now, let's say it's negatively charged. Let's say it lost all its positive charge. So object A is now negatively charged. I can have a second object peacefully in its corner. And this object is neutral. Now, neutral simply means it has equal amounts of both types of charge. So overall, it has zero charge, zero net charge. It's neither positive nor is it negative. If I now move this negatively charged object closer to my neutral object, what will happen is that the negative charge on object E will attract or pull all the positive charge to this side, and it will repel all the negative charges over here. Now, if you bring it close enough, if you bring A and B close enough, like if you make them physically touch, you might have some balancing of, well, movement of charge. That's what I'm trying to say. But anyways, that's beside the point. B now has two distinct regions after you brought A close to it. And these two distinct regions are, you have the positive charges over here, and on the other side you have the negative charges. Now, it is not that B has an overall charge, but it is that B has these two specific regions of charge, and this is charging by induction. Now, static electricity can produce the next type of electricity, which is current electricity. If you have enough charge built up in a single place, it will want to move. There is this interesting thing in nature where everything tends to want to move to a place of balance, and charge is one of those situations. It will want to balance itself out. Negative charge is looking for positive charge. Positive charge is looking for negative charge, because that's just their nature. Now, this brings us to electric fields. Electric fields. So, if I have a positive charge, a single positive charge, there is an electric field around it. This electric field is the region around this positive charge in which the positive charge will influence other charge or affect other charge. And the electric field around a single positive charge looks like this. If I have a negative charge, a single negative charge, the region around a single negative charge will look like this. Oh, I put that arrow in the wrong direction. My bad. Good. If I bring a negative and a positive together, so I have my negative over here and I put a positive over here, it will look like this. Now again, these are just sketches, right? These are just meant to give you a general idea of what the shape of the field is like. Please don't think that these diagrams are actually literally physically how the field is. This is just to give you an idea of shape. That is all. Alright, that's literally all. So this is what happens when you have two opposite charges next to each other. Now if I decided, why did I do that? If I decided to use two positive charges next to each other, it would look like this. Dum 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 dum. Again, you might find diagrams drawn with more detail elsewhere. That is not a problem. The idea is the general shape of the field. Right? You don't have to exactly replicate the diagram. And I need to point something out. Here we have attraction, A-T-T-R-A-C-T-I-O-N. Attraction, right here. If you look at it, it's as if the negative charge is pulling the positive charge towards it. Over here we have repulsion, P-U-L-S-I-O-N. It's like the two positive charges are pushing each other away. So opposites attract for this reason. Well, opposite charges. A negative charge seems to be pulling a positive charge towards it, and a positive charge seems to be pushing another positive charge away. This brings me to yes, uses and hazards of static. So static electricity, well, I should start with the hazards first. H-A-Z-A-R-D-S. First of all, when static electricity builds up, you can't see it. I'm sure we have seen many lightning strikes. We've been in many thunderstorms. You look outside, all you see is clouds. You can't tell where in the cloud the charge that causes the lightning is hiding. You cannot see it, okay? For this reason, we only know static is present until it discharges. So the first hazard of static electricity is most times we can't tell that it is there. We just don't know. Secondly, discharging, or like I said, positive charge is going to look for negative charge because it wants to balance itself out. Negative charge is going to look for positive charge because it wants to balance itself out. That process is called discharging, right? Discharging is random. You can't tell the charge when to move. You can't tell the charge where to go when it decides to move. The charge will do so without your permission, because charge is a big man and the charge don't care. Genuinely does not care. For this reason, excuse me, static electricity is very, very dangerous. You have no control over it, none. The most you can do is provide ways and means for it to not build up in the first place, or if it builds up, it discharges before it becomes dangerous. If you've ever, like, you held a balloon at a party and you rub the balloon on your shirt and you move your hand over the balloon, you kind of feel the hairs on your hand stand up, that's static electricity. You've unwrapped a package and the plastic, it's not sticky, but it clings to your hand. That is static electricity. It does not follow any rules you set for it. It does what it wants. And because discharging is random, it can damage you and it can damage equipment as well. So, uses of static electricity, yes, it is useful. Sometimes. It can be used in dust filtration. It can be used in printers, printers. The paper and the ink have opposite charge, and as a result of which the ink clings to the paper. I was about to say the paper clings to the ink, which would be hilarious. Crop dusting. Even in some cases, spray when you're painting vehicles and you're using spray paint, not the cans, the machine that turns the paint into a very fine mist. If the paint has one charge and the or whatever you're painting has the opposite charge, the paint will cling to the object you're painting. These are just some of the uses of static electricity. I will end the video at this point because the next thing we have to move on to is current electricity, and I don't want the video to end randomly after just introducing the topic. As always, please like, subscribe, comment, of course share, especially now at exam time. Thank you once again for the support, and I will see you in the next one. Bye bye.